Welcome to Algebra 2, Unit 3, Lesson 1, Modeling Multiplication with Area. We are about to start a unit that will focus on factoring, and we're going to park ourselves in factoring for a while. The strategy that we're going to use to model our factoring is something called an area model. And I think the best way to experience that model to start off with is with multiplication. So multiplication is like our forward direction, factoring is like going backwards. And so we want to get good going forwards before we start going backwards. And so this lesson is going to focus on what this model is, why the model works, and how to use the model for multiplication. So the lesson goal is to model binomial multiplication with area. Now that got a little bit mathy sounding, so we'll talk about what these words mean. I think I have them on a future slide, but binomials are just algebraic expressions, and we're going to model that using area and to appropriately use the vocabulary associated with multiplication. Vocabulary is so important. If you think about how many times when you're reading the directions for something, what are you supposed to do? You need to know what the words mean. So if the directions ultimately say multiply or factor, you need to know what those words mean so you can execute the procedure correctly. So I want you to consider the problem 3 by 5, or 3 times 5. It's another way to say it, but 3 times 5. Okay, so think about that for a second. We know that the answer is 15. At least I hope we know that the answer is 15. 3 times 5 is 15. But how can we model this using the area of a rectangle? So even though I know that you guys all can say 3 times 5 is 15, what we want to focus on, especially on this slide, is the model. What does 3 times 5 look like when you're looking at it on a rectangle? So we're going to look at this picture. Okay, so this is a 3 by 5, which is why it dumped out of my mouth that way a second ago. 3 by 5 rectangle. And you can see that we have 3 units on the vertical here, and 1, 2, 3, 4, 5 units on the horizontal. And essentially what we're asking is, what is 3 times 5, or what is 3 5 times? And so you could do this by adding up the threes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. All right. And so we know 3 times 5 is 15 because this 3 by 5 rectangle here has 15 squares in it. And literally multiplication is just a faster way of adding all those up. Okay, 3 5 times. Now, this is actually the same rectangle, except turned sideways. And so now we have our 5 on the vertical here and the 3 on the horizontal. And you might think of this as 5 3 times. And once again, multiplication is just a shortcut way of adding all the squares up. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. What I want you to notice there is that the orientation of the rectangle does not matter. Okay, both of them have the same area. So when we're finding the area of a rectangle, essentially what we're doing is we're like counting up how many of the little 1 by 1 squares will fit inside the rectangle. That's what area is. It's why area is different from length. But the orientation of the rectangle does not matter. So you can do 3 by 5 or you can do 5 by 3. Now I want you to keep that in mind, because when we start doing that with the algebraic expressions, it's maybe not quite as obvious. So I have written over here, this demonstrates what's called the commutative property of multiplication. That is 3 times 5 is equal to 5 times 3. So that's a property that most of you know. You might not be able to pull the word commutative out all the time unless you've seen it recently, but it is a critical property of multiplication, that you can multiply in any order. And the area model gives us a way to see that. And so while it might be obvious to you with the 3 and the 5, when we start putting algebraic expressions in there instead of 3s and 5s. It might be a little bit less obvious, but I do want you to keep that in mind. It does not matter which order you write them in or the positioning of the expressions along the x or vertical or horizontal sides of the rectangle. So we use the little boxes to illustrate the rule, and once we know it, we stop drawing them. So for example, find the area of the rectangle below. So back in maybe elementary school, middle school somewhere, you might have started finding the area of the rectangles by doing like counting all the little boxes. But once you know how this works and you do, 7, 8, 10, I don't know how many problems you need to do, you begin to realize that the area will always be the base times the height. Sometimes you'll see it as length times width. What words you use there aren't as important as the concept, which is you multiply the two dimensions together. And so we would say the area of this rectangle is 4 times 6 or 24. Okay, and we can verify that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. And again, all multiplication is repeated addition, but nobody wants to keep adding that together all the time. And so we develop our times tables and we just memorize them. It is still important to know what times tables are. Okay. So, there's going to be another rectangle below. So let me take a second. Let me erase that. I'm just going to move it so that it is, we'll move it over here. 4 times 6, and that is 24. So a little quick practice problem. 3 by 7. So take a moment. If you're following along at home for this lesson, take a moment and do that out. And hopefully you know that the answer is 21. 3 times 7 is 21. Okay, times tables are one of those things like you can use a calculator, but it slows you down a lot. So if you sort of know your times tables, but you're not super confident, it actually would not be a bad thing for you to practice. Okay, so let's consider how we could break that last problem up. Now, I have a disclaimer here because somebody's going to be like, wait a minute, how did you do that? I am breaking these numbers up in an arbitrary way to illustrate a point. There isn't a system for how I did it. So basically, I'm going to break them up in just whatever way I feel like breaking them up. I'm not doing a procedure, and I wasn't looking for a particular way to break them up. I just kind of picked a way to do it. So here's what I mean. 7, I could break up into 3 plus 4. And 3, I could break up into 2 plus 1. Now, with the 3, 3 is a fairly small number, so we're kind of limited in how we could break it up. But 7, like if you're wondering, well, why did you pick 3 and 4 and not 6 plus 1 or 2 plus 5? I could have picked 2 plus 5. I could have picked 6 plus 1. I just picked 3 and 4 because I want to show you something. So if you'd like to watch this presentation and then redo the example with some different numbers in it, knock yourselves out. It actually is not a bad idea. So this is our 7 by 3 rectangle that we had before, except now we can see the breakdown of the squares. And what I'm going to do is kind of break this down into 3 plus 4. So I'm going to kind of emphasize that line right there. And then 2 plus 1. Okay. Whoops, that got a little bit messy there. 2 plus 1. Okay, now again, I could have picked different places to put this line. Now, if I look at it this way, I have 3 plus 4 here, and then 2 plus 1. So if you're having trouble seeing what I did, what I did was I broke up the 7, and instead of counting like 7 all the way across, I broke it up into 3 plus 4. So we have 3 boxes, and then 4 boxes together, we would get the 7. And then here I had the 3, and I broke it up into 2 boxes and then 1 box. Now I want you to watch what happens when I find the area, and you got to watch the screen here, of each of these individual boxes, these individual rectangles. Okay, so this rectangle right here has a height of 2 and a width of 3. So the area of this rectangle is 6. This rectangle here has a height of 2 and a width of 4. Okay, so 2 by 4 is going to give me 8. This rectangle here has a height of 1 and a width of 3. 1 times 3 is 3. And then this rectangle right here has a height of 1 and a width of 4, so it has an area of 4. And if I wanted to find the area of the entire rectangle, okay, I'll box this like the entire rectangle, I could add up the individual areas. So I could do 6 plus 8 plus 3 plus 4. And I'm just going to employ a couple of properties of addition. I'm going to do this. I'm going to do 6 plus 4, because 6 plus 4 is 10. And then I'm going to do 8 plus 3. 8 plus 3 is 11, and then 10 plus 11 is 21. Now, could I have grabbed a calculator and done that? Sure. But if you're wondering, why did I do that? It's because pairs of numbers that add up to 10 are easier to keep track of. So I could have done 14 plus 7, which also adds up to 21, but 14 and 7 are harder for me to add than 10 plus 11. So I just kind of look for things that add up to 10. So that was just the only reason I did that. Now, let's see. I have something, and I can't see it because it's super small on the screen next to it. Okay, note that breaking it up does not change the overall area. So you can like break your length and your width up into like its constituent parts, and it wouldn't change it. So like I said earlier, if you wanted to take this slide and redo it and split the 7 up a different way, split it into 6 plus 1 or 2 plus 5, and just see, you'd have different numbers like in here, but it wouldn't affect the overall area. Okay. And we notice that 3 plus 4 times 2 plus 1 is equal to 21. Now, part of why I did that was to change the notation so that the notation looks more like what we call binomials, okay? And I'm going to define that on the next slide. So key vocabulary here. This is a formula from middle school geometry. The area of a rectangle is equal to the base times the height. I probably should have used a lowercase b there. I'll try to edit that on the actual one in class. I think it just defaulted to a capital B. It probably should be lowercase b there. And the reason for that is mathematically, like one of the math conventions is that like capital B stands for area of the base of like a 3-dimensional object, and lowercase b is the length dimension, okay? B and H are what are called the factors, and the area is the product, okay? So the dimensions of the rectangle, the height and the base, are the factors, and the product is the area. Now, that may or may not help you if you don't know what those words mean. So factors are things that are multiplied, and the product is the result of multiplication. So factors are any things that are multiplied. So for example, if you had 2 times 6 equals 12, okay, these guys would be factors. The 2 is a factor, and the 6 is a factor, and the 12 would be the product. And you're going to hear those words a lot. In fact, the word factor, you will hear it as both a noun and a verb. So when we're talking about factor, the noun, What we mean are like the actual things, numbers, expressions, variables, whatever, that are being multiplied. When you hear the word factor as a verb, it means find the factors. So if somebody says factor this number, what they're asking you to do is find the factors. Okay. Now, I know that the vocabulary can be kind of dry, but we really have to know what these words mean so that when we read the directions or when you're listening to mine or anyone else's presentation on this, you understand the words that are being used. So we're going to extend this to binomials. Binomial is kind of a scary sounding math word. A binomial is simply an expression with two terms. And then what seems to happen a lot in math is I can define binomial as an expression with two terms. And then we now have another vocab in there, like word in there. Do we know what terms are? Great, a binomial has two of them. What are they? It doesn't do any good to know that a binomial has two terms if we're not sure what terms are. If factors are things that are multiplied, terms are things that are added or subtracted. Now, technically, there's no such thing as subtraction. Okay, so if I had 7 minus 5, I could write that as 7 plus -5, and I could rewrite it as an addition problem. Okay, oh, it's like really weird how there we go. It's like my face is going off the side there. It's just where my laptop is on my lap. Okay, so factors are things that are multiplied, terms are things that are added, but we usually don't change the minus to a plus negative. So a lot of times when we talk about it, we'll say added or subtracted. So here are some examples of binomials. Okay, oh, and before I leave this, the prefix bi means two. And so you can go back to what you know about words to remember what this is. Bi means two. So a binomial, you're looking at two things that are being added or subtracted. For example, 3 plus 4 is a binomial. It's a simple example, and most of us would just go ahead and write 7, but technically 3 plus 4 meets the definition of a binomial. Now, usually a binomial has a variable in it, and so we can't carry out the adding or subtracting, so x minus 7 would be an example of a binomial. Or you could have 2x plus 3, where the terms are 2x and 3. And you might be saying, but wait a minute, Miss Taylor, there's multiplying happening here. Isn't there factor or these factors? Here's what's happening. You've got 2 times x. 2 and x are factors of 2x. And 2x is a term along with the number 3. And so you have two terms, and this term over here on the left can be factored. Okay, again, that fluency with the vocabulary there is going to go a long ways just to understanding the lesson. So we have these binomials. So what we're interested in, and I actually don't know what's underneath there. I think it's the 3. So we are interested in problems that look like this. So I know my face is covering some of it. So x minus 7 times 2x plus 3. So how can we multiply things that look like that? X minus 7 times 2x plus 3. Now, there are at least 3 different ways that I know of to do this. We're going to be using in this class the area model. Now, full disclosure, I was not taught the area model. I was taught how to do this by distribution and with an acronym that many of you might know called FOILing. There's nothing wrong with FOILing. We're just not going to be using it in this class. We're going to be using the area model. And the reason I want you to use the area model is because when we go backwards from multiplying, the area model is going to help you visualize it. So we're going to practice with the area model, even if you know another way to do it. So let's model this with the area model. So again, remember from when we did like the 3 times 5 and the 5 times 3. It doesn't matter where we put these factors. And I think I have an example coming up where we'll just illustrate that so you can see it. Like you can see it done both ways. This is where, like, if you're working with your friend, there's two ways to set up all these problems. If you and your friend set all of them up all the same way, maybe that can happen because you just kind of get in the groove of it. Just don't copy if you don't know what's going on. So I'm going to go ahead and do x minus 7 on the vertical, and we'll do 2x. And you could put the plus 3 there if you wanted. Most of the time, we'll just write the 3. And now what we're going to do is find the area of each individual box, okay, by doing base times height. Okay, so we're going to do the area is equal to the base of the rectangle times the height of the rectangle. So right here, I have x times 2x because the rectangle is x tall and 2x wide. So x times 2x, okay, is x times 2 times x. And I'm going to play with that commutative property, 2 times x. I'm going to do it the other way around. Hang on. Right here, we're going to do x times 2 is the same as 2 times x. Okay, because that's multiplication. X times 2, 2 times x. I can go ahead and switch the order here. X times x is x squared. So that inside there is going to be 2x squared. That was maybe the trickiest one to do. And normally, most of you will do this in your head. All right. I expect you to do that in your head. You do not have to write that out. I am just making sure that before any of you leave this lesson, you know where the 2x squared came from. All right. Next box, I have a height of x and a width of 3. So 3 times x is 3x. Next box down, we have a height of -7 and a width of 2x. 2 times -7 is -14. So that is -14x. And then in the last one here, +3 times -7 is -21. And just like in the example where we had the 3x7 rectangle, we had to add up all the individual areas to get the area of the whole thing. Because remember, I'm not looking for the little areas, I'm looking for the area of the entire rectangle. So to add that up, we would have 2x squared plus 3x minus 14x minus 21. And we can combine these terms to get 2x squared minus 11x minus 21. You are welcome to use a calculator at any point during that process. Most of you will do most of this in your head though. So you would do this work over here in your head, and you would also combine these in your head. So you'd be like, oh, -14 plus 3, or you'd grab your calculator and do -14 plus 3, and you'd get the -11, and you would just go straight to this line right here that I'm sending my laser pointer over, okay? You do not have to write that out. Okay, I'll try to, on the next slide, do it more like what I would expect you to do. And that's how the area model works. So example 2, we have x plus 3 times x plus 5. I didn't realize my rectangle was quite so close to the problem there. But let's go ahead and do x plus 3, and then we have x plus 5. X times x, so we're finding this rectangle right here. X times x is x squared. X times 5 is 5x. 3 times x is 3x. And 3 times 5 is 15. And then most of you will do this part in your head. You will not write it out. So you would just say, okay, the total area is x squared plus 8x plus 15. And there is your product. So again, just to reemphasize, one of the factors is x plus 3. The other factor is x plus 5. So there are two factors. And this is the product. It is the result of the multiplication as modeled on an area model. Now, the next slide is going to ask us, like, does the order matter? So notice that I put the x plus 3 on the vertical and the x plus 5 on the horizontal. And so we just want to quickly make sure that we know that it doesn't matter. So I could put x plus 3 across the horizontal and x plus 5 on the vertical. And we would have x times x is x squared. X times 3 is 3x. X times 5 is 5x, and 5 times 3 is 15. And 5x plus 3x is still 8x. And so x squared plus 8x plus 15. And so it does not matter. That goes all the way back to that beginning rectangle. We had like 3 times 5, and I could put the rectangle like this way or this way. Okay, and it didn't matter, they were going to have the same area. Now, this is going to come up when you guys are doing your factoring, because depending on like where you put, like say the 5x and the 3x, some of you are going to put the 5x up here and the 3x down here, and some of you are going to put the 5x here and the 3x here, and you're going to wonder, does it matter? Does it matter which one of those x's I put in which position? No, it does not matter. And here's why it doesn't matter. It doesn't matter because multiplication is commutative. It's just going to change whether you get the x plus 5 on the left side or whether you get it across the top, but it's not going to change your final answer. Okay, so what's left? So we've gone through what the model is, how the model works, the vocabulary associated with the model. Now you just need to do some. So there are 3 practice problems. We are going to be collecting these for a classwork grade. And even if you know how to do them using foiling or using like there's a vertical method for multiplying, I don't want you to do that because I know what the next lesson is going to be. And I know that the area model is going to help you with the next exercise. So I really want you to do these out. Now, if you are doing this in class, okay, or if you're doing it at home and you're like, this is super easy, I learned it this way in Algebra 1 and I'm done with them already. If you finish early, I want you to consider how this one relates to the second example. So the second example was x plus 3, x plus 5. Okay, what's the same about the problems? What's different about the problems, and how does it affect the answer? Because when you have lots of similar pieces in the problem, then you might expect to have some similar pieces in the answer, and I think that's worth looking at. Okay, so that wraps up this lesson. As always, you guys know where to find me, and let me know if you have any questions.